We are returning to the AI Symposium, and welcome back here. Other people will be straggling in and they will miss a highlight of this show. So you can give them a very hard time. So it's my great pleasure to introduce Qianqian Wang, who is currently a postdoc at Berkeley and got her PhD at Cornell and has been doing all sorts of wonderful things which she will tell you about.
Okay, great. Thank you for the kind introduction. And it's my great pleasure to be here. And today I'd like to introduce some of our recent work on recovering the structure of the dynamic 3D world. So basically, we live in a 3D world that is full of all kinds of motion. And as humans, we constantly receive, we're able to perceive the 3D environment very well, despite receiving only 2D signals as input. And this is actually very incredible because this involves constantly solving an inverse problem of recovering the most plausible 3D arrangement among all possibilities. And this allows us to, interact with our 3D environment and perform all kinds of tasks. So as a computer vision researcher, the question I'm pursuing here is it possible for machine to achieve something similar? So recently, over the years, we've seen great progress in modeling the static 3D world. For example, we have CoMap that can estimate the camera poses and sparse scene structures. We have NERF that can turn pose images into a dense 3D scene representation for novel view synthesis. These are all great, but there is a fundamental assumption here, which is all of the views are consistent in that they observe the same 3D structure. And that assumption doesn't hold for dynamic scene because now the scene is moving. And here, for every time step, we have a different underlying 3D scene, and we only have a single observation per time step, which makes the problem very, very kind of under constraint. So now let's see, in order to kind of reconstruct a dynamic 3D scene, what does it mean? What does it take? So I think it involves solving several components. The camera parameters, the geometry of the scene, and also the motion within the scene, right? So, and today I'd like to focus on the scene motion because it is very crucial for us to understand what's going on in the scene. And it's also something that we don't exactly know how to model yet, even in the 2D domain, not to say in the 3D domain. Okay, so now let's look at some of the existing 2D estimation methods. We have feature tracking, which gives us long-range tracks, but they're only very sparse. On the other hand, we have optical flow that gives us dense motion field, but they're very short range. And neither is ideal. And what we want is something that is both dense and long range. And that is the problem that we're trying to solve in this ICCV23 work, where the problem set up here is that we have an input video, and we want to optimize for a global motion representation, which we call OmniMotion. And we hope that OmniMotion can capture the complete information of the motion within the video. And that means that you can query any pixel and obtain the motion from any pixel in any frame to any other frame. And here we're only showing the motion trail for a few sparse pixels in the first frame, but you can actually query any pixel arbitrarily. Okay, so how do we achieve this? We actually leverage intrinsic properties of the visual world. And the first property we use is cycle consistency. So even though this person moves within the video, but it is still the same person, right? So at the point level, at the pixel level, all of the 3 points here represents the same visual entity. Or you can say that they should correspond to the same point in some canonical space. And they should be globally cycle consistent with respect to each other. So that's the first insight that we have. And the second insight is that we actually need something that is 3D to handle occlusion. Because in this case, the person's foot is occluded in the second frame, and both the foot and the occluder occupy the same pixel. So in order to tell them apart, we need an additional z dimension that can tell different surfaces that kind of locate at the same pixel apart. And even though this sounds very obvious, but this is not what people do in the past. Okay, so specifically, this is how we model the problem. We have a canonical 3D volume, and we have a set of local to canonical bijections that models the kind of invertible mapping between the shared canonical 3D volume and all of the local 3D volumes. And we store the color and density in the canonical volume. And together, this representation ensures global cycle consistency because we have this bijective mapping. And it also allows tracking through occlusion because we model the scene, model motion in the 3D space instead of 2D. And here are just some results where we track a few pixels in the first frame, but this representation allows us to track any point in any frame to any other frame. And here, on the left-hand side, you can see that our method can actually track through occlusion very well. And this also is enabled by this underlying 3D representation in our method. So another interesting thing about this method is that depth ordering naturally emerged from this representation. So here we're visualizing the kind of depth rendering from this representation, and you can see that the ordering between surfaces are actually very meaningful. And this is because depth and occlusion, they're actually two sides of the same coin, meaning that if you have occlusion cues, that actually tells you how different surfaces are ordered, right? And on the other hand, in order to correctly model occlusion, you also need to understand the depth ordering of different surfaces. And our representation allows this same, those two problems to be solved at the same time. So if we get one right, we automatically get the other. Okay, so far we talked about 2D motion. And given all of the great progress in the field, we really want to upgrade them to the 4D world. And here 4D means 3D plus time or dynamic 3D. So in this work, we try to recover a full set of 3D properties from a single video, which includes the camera parameters, the persistent 3D geometry, and the long-range 3D motion of the scene. As you can see that we can render novel view in real time. We can visualize the long-range 3D tracks. And the way we do this is basically, because the problem is very kind of under constraint, we actually leverage lots of data-driven prior, like long-range 2D tracks and mono depth estimators, and we also have a low-dimensional motion representation that further constrains the optimization problem. And here are just some more results. So moving forward, I think there are actually two kind of big part of methods in the perception system. And the first part is the learning-based method, like mono depth estimator, that can give you some estimate about the scene property in a feed-forward way. And the other type of method are more like the method that I talked about today, that is more about modeling the scene. It's like a pipeline that leverages the data, the data itself to produce some understanding of the scene. And I think there is actually a very nice connection between these two types of methods in the sense that learning-based method can provide priors for the modeling method because this modeling, this 4D reconstruction pipeline really need a lot of data-driven prior. On the other hand, modeling can actually provide annotations for your learning problem because they can really leverage the internal information within the data that you're trying to optimize. So basically, I think we need both better learning-based methods that are more scalable, that can leverage the vast amount of unlabeled video data for training. And on the other hand, we also need better modeling-based method, which means we need better scene representations and more robust pipelines that can produce these annotations for in the wild videos. And if both can improve, then I think the 3D perception pipeline or system can get a lot better from now. That's it. Thank you.
I think we have time for a question or two.
Very cool results. I was wondering how accurate the depth estimates are in the last project. It's really interesting you're able to do all these things at once, like depth and tracking. And I'm curious about that dimension of the project.
Right. I think that they are pretty accurate, and they are getting more and more accurate like every day because there are more work coming up. So I think the quality is pretty. I think it's enough for doing some kind of actual 4D reconstruction. Yeah.
Would it be good for construction as well as reconstruction? So for instance, instead of having to render a video game, you could just use that to create an environment. Would that be useful for it, or?
Right. I think in order to create a game from this, there are just a lot more things that you need to do. For example, you need to make it actionable. Like you have to be able to interact with your environment. But right now it's more like a passive reconstruction. So I think it would be very, very cool if we can make it a video game. But I think there are a lot more to be done. Yeah.
Okay, let's thank Qianqian. And our next speaker is Guanya, who is currently an assistant professor at the Robotics Institute at Carnegie Mellon, was previously a postdoc at Washington, and was previous to that a graduate student at Caltech. And he's doing all sorts of fabulous, fascinating things.
Thank you, Ben. Let me share screens now. A second. Very excited to be in beautiful Michigan today, presenting some of our recent research. If you're interested in the slides, you can scan the QR code to get a PDF copy if you're interested. And the title of today's talk is Building Generalist Robot with Agility via Learning Control, Humanoid and Beyond. And here are some teaser videos. The first one is Humanoid Robotic Control project called Omnitrol. And the second one is sampling-based model-predict control for contact-rich problems called DEL-MPC. And the third one is a safe, high-speed locomotion project called Agile but Safe. We will get into these details very soon. All right, let me start the talk by some recent trends in general-purpose robot. It seems like in recent years, general-purpose robots are really taking off, right? Especially humanoid. There are many investment and startups. Here is just a partial list of humanoid companies, right? And there are also a lot of big players like Tesla and NVIDIA, as we know. So what is general purpose robot? And a common definition is a robot that can do many different tasks in many different environments. For example, here are some humanoid skills from the Omnitrol and the Vococo project in my lab. There's one robot which is unique to each one, can do very diverse tasks. On the top left, it can play tennis. On the bottom left, it can interact with human, give you a handshake, or give you a hug. This is powered by GPT-4o. And on the right top, it can do some fun dancing. And on the right bottom, it can do this kind of continuous parkour style jumping, right? So one robot can do many different things. I mean, you can argue, right, in all these applications, there exists some other robot can do this maybe better than humanoid, but it's a single robot that can do many different tasks. Similarly, right, another example is the Mobile Aloha project from Stanford. And in Mobile Aloha, a mobile manipulator can do many household tasks like cook shrimp for you, rinse pan, high five with you, or push chairs, right? A single robot can do many different things. In my opinion, there are two aspects or two axes defining useful general purpose robot. The x-axis of this figure is the generalist aspect, or the breadth of task and environment. For example, how many tasks the robot can do and how many environment the robot can handle the task. For example, for mobile manipulator, you need to work in different kitchen. For Lego robot, you need to work on different terrains. And the y-axis of this figure is agility aspect, or the depth in task execution. That includes how fast the robot can do the task, how accurate it can do the task, right? And also dexterity and reliability. I may abuse the word agility a little bit here, because agility here not only refers to physical agility, also means something like precision, dexterity, and safety. So ideally, we want both, right? And each bar here corresponding to either a task or environment. And the dashed line is roughly human performance, right? We want a robot that can do many different tasks better than or close to human. It sounds very hard, right? But an interesting fact is in natural language processing, large language models have roughly achieved that, right? Large language model can outperform classic method and humans in many different tasks. For example, machine translation, summarization, right? So how about robotics? In terms of balancing between generalist aspect and agility aspect. And it seems like there are some trade-offs. on the one hand, there are many amazing works focused on agility in some specific tasks, but with limited generalizability, corresponding to this figure. And for example, back in 1990s, Chris Atkinson and Stephen Shaw already achieved humanoid juggling. It's almost 35 years ago. And it's still very impressive in my opinion, right? It's very agile, very precise. And another example is this super high-speed pen spinning from Ishikawa lab in University of Tokyo. And this is almost like 20 years ago, basically. And the first few seconds of the video are actually real time. So the pen is spinning super fast. And you see the slow motion. You can actually see that all three fingers coordinate with each other. It's very smooth, very agile, very precise. And it's vision-based. It don't have any mocap, whatever. It's vision-based end-to-end. And another example, everyone knows that, right? Is like the humanoid parkouring from Boston Dynamics, right? The robot can do this very precise, very agile parkouring. It's still one of few humanoid that is physically more powerful than human, right? The slow motion is beautiful here, right? You can see there's very precise, very agile motions, and whole body motions, right? So, however, right, this method in general have limited generalizability. Right, for example, if we zoom in what happens here in the lower bar, right? Something like this. The same robot that can do parkour, right, can also do some interesting mistakes. In this video, it thought it got the card, but actually didn't got the card. And it failed, because it's a kind of like interesting feedback, right? Yeah, I mean, again, it's the same robot that can do parkour, right? Definitely beyond infant level, right? But this is like, something probably 2 years ago can figure it out, right? If he or she is tall enough. So on the other hand, right, we have amazing progress in the generalist world corresponding to this figure, right? All the tasks are doing pretty good, even though it's still a little worse than human. System like robotic transformer from Google DeepMind can do hundreds or even thousands of tasks, right? Like in this video, it's really a lot of tasks, grasping different objects in different kitchen, things like that. However, I would argue that most of the tasks in this video are not very agile, or like much less efficient than human. For example, grasping a can take like 20 seconds. So an interesting question is, can we get there like human performance using skilling law? By collecting like a lot of demonstration data? I don't know, maybe yes, if we have enough data, but the problem is that in the near future, we won't get GPT level amount of high quality data like this in robotics. All right, so how do we tackle the challenge? How do we build generalist robot with agility, like in this figure? I mean, it is a super challenging problem, which apparently I cannot tackle today, but I would like to share some recent thought with you today. So in my opinion, on the agility axis, the y-axis, physics and dynamics really matters, like physics and dynamics. So the first key idea to this talk is better use of physics and dynamics. So can we combine learning with structure and ideas from model-based control and physics to achieve something called structure scaling, scaling some structure. And on the generalist aspect, the x-axis in the figure, I think scaling really matters. It's not just how to scale, but also what to scale, right? So the second key idea of today's talk is better use of scaling. Can we do both offline scaling with learning and online scaling with adaptation, planning, and optimization? That's basically the two message I want to convey today. Okay, great. The technical outline today. The first part, we're going to talk about like a versatile humanoid whole body control using sim-to-real model-free reinforcement learning. Because in my opinion, sim-to-real model-free RO is a straightforward way to combine physics, dynamics, and scaling. Because you train a policy offline in physics-based simulation, right? And using deep reinforcement learning, and you transfer the policy to the real world. And in the second part, we will discuss the limitation of such a framework and how to go beyond it via learning control. Specifically, there are 3 different levels. In the dynamics level, we're going to learn dynamics from the real world or learn a world model, whichever we want to call this. On the policy level, we're going to talk about structure and hierarchical reinforcement learning control. And finally, in the program level, we neither learn dynamics nor learn policy. We use ideas from learning to improve existing control program, like model predict control, MPC. All right, let's get started from part 1. The first project I would like to introduce is called H2O, Human to Humanoid Whole Body Teleoperation. The goal of this project is to build an interface between whole body human and the humanoid motion. And on the teleoperation side, H2O enable very diverse teleoperation interface from VR, RGB, verbal, exoskeleton, whatever. And on the autonomy side, H2O enables some level of autonomy via either learning from demonstrations or integrate with foundation models like GPT-4o. And this is fully open source from training to hardware deployment. If you're interested, check out our repo. It's fully open sourced. Okay, before talking about the details, I would like to show a video, kind of like the teaser of the, yeah. So the interesting, the first thing it does is make itself off gantry. It's like almost a joke. And again, it is whole body control. It's not just like lower body, it's upper body, right? It's whole body. And also like 2 6-stop hands. So the robot human here is basically following a VR, is controlled by VR using a human. And it's gonna walk to this bench and grasping a knife here. It's a little bit scary, but trust me, it's fun. It's going to cut a cucumber, not you know, yeah. Right, and after it does that, it say hi to you, and it's gonna sweep the floor, take a step back and sweep the floor. So this is basically like a one-shot video to show, you know, it's a general purpose, right? It can do locomotion, can do local manipulation, can clean the floor, you know. Yeah, and also say hi again to you. Yeah, I can do many manipulation like watering the plant, moving basket, many different things, playing tennis, table tennis, badminton, different sports, and boxing, drawing letters, local manipulations. And this is like a GPT-4o enables, you know, give you a hug or like play boxing with you. Autonomy. This is autonomy. We learn a diffusion policy from data to achieve this kind of autonomy from teleoperation data. And this is like verbal instruction. We literally talk to the robot. Can you turn to the right? See you next time, bye-bye. And the robot will respond. And this is like, you know, for robot learning paper, you have to bully the humanoid to prove it's robust. And it's all the outdoor locomotion. So it's a single neural network, single policy can also do this outdoor locomotion. Okay, sorry, the video is very fast, but if check out the website for more details. And also it's open source. All right, how do we do that? So first, why is this hard? Because teleoperation is not new, right? In tabletop manipulation, it's been many years. Why is it hard for humanoid? I mean, from the agility aspect, it's pretty hard because high-dimensional whole body control, right? You basically need to handle lower upper body coordination, you know, as mentioned by Karen, is non-trivial, right? And need like, for a human, need 18 months of learning, right? And from a generalist aspect, right, the system need to track infinitely many diverse human motion in real time, infinitely many, right? You need a very strong generalizability, right? All the motion in these figures are different. So the key idea of H2O is scaling, right, in sim-to-real reinforcement learning. So we basically did sim-to-real RO from large-scale retargeted human motion data set. So the step one is to create a large-scale humanoid feasible motion data set. We start from a huge human motion data set called AMAS in the front vision community in the first row, corresponding to the first row in this figure. And in the second row, right, we convert the original AMAS motion to a human model that is closest to the humanoid robot, just using inverse kinematics to get the second row. However, right, the second row, the translation in the second row is purely kinematics. It's not aware of embodiment, it's not aware of dynamics, and could be infeasible for humanoid. So the third row is actually very important. We call this physics-based retargeting. Right? We basically learn a privileged imitation policy, the pink policy in this figure, to track all the motions using model-free RO, right? And this policy is called a privilege because it knows all the state, including those unavailable in the real world, right? And this procedure generates humanoid feasible motions in the last row and filter out impossible motions. Right, for example, the last motion, the acrobatic stuff is infeasible, we just remove it, right? And the first four are part of the data set. This procedure basically gives us a data set that is humanoid feasible. And the second step is sim-to-real. is sim-to-real reinforcement learning. And more specifically, once we have the privilege imitation policy, the pink policy in this figure, we distill it to a deployable policy, the blue policy, in simulator using supervised learning, basically Dagger. Yeah. And the deployable policy, the blue policy, only knows state available in the real world. It is very practical. And with 3 key points as the motion goal, 1 head and 2 hands, as shown in the red figure. We use a very sparse motion goal to make it, general for all different type of teleoperation interface, like VR, RGB. They all can give you this 1 head and 2 hands information. And finally, right, to make it sim-to-real, to make it robust, we did a lot of documentation to make sure the robot can actually do sim-to-real. Yeah, this is how it works. And another product of H2O is we released the first humanoid whole body teleoperation demonstration data set, which includes 6 different tasks. And with such a data set, we train a diffusion policy to learn from these human demonstrations. And here are some simple catch and release results. To be honest, this result is still very simple. It's just like not long horizon, just like simple catch and release, but it's whole body. Again, it not only learned the upper body, it learned how the lower body need to support or something like that. Okay, and as you can imagine, H2O can also easily be integrated with multimodal frontier models like GPT-4o. And the prompting is very simple due to the small embodiment gap between human and humanoid, right? The prompting is just like field length. You just tell the GPT, okay, you are a humanoid, there's something you can do, blah, blah, blah. So this is the video, and the input to GPT-4o is image and robot state. And the output is desired robot key point positions or motion primitives. And here the GPT-4o decide, okay, you understand you want a hug, and it commands the robot to open the arm and give you a hug. Yeah. It's fully autonomous, powered by this foundation model. And and understand you want to sit by, and it wave the hand to sit by. Yeah. All right. This is like H2O. Another project I want to introduce in part 1 is Vococo, learning whole body control via sequential contact. So H2O tried to learn from human motions, right? It's trying to learn from human motion. The Vococo is basically the opposite, another extreme. So Vococo is trying to learn versatile, agile whole body skills without any human motion priors. So we want to figure out what is the right way to do RO without human motion priors in long horizon contact-rich problems. Due to the time limit, I cannot go to the details, but the high-level idea is we decompose a long horizon task into a sequence of contact goals and task goals. And this decomposition really enables task-agnostic reward designing and skill learning. And this is like a video. In simulation, it can do this very interesting parkouring stuff, single-like. In the real world, we can transfer some of them like this, consecutive jumping, like 2-step jumpings, pretty stable, and it can do this funny clamping dance for you. I should have the video. You can hear the clamping. It has contact with, yeah. And it can also do this bidirectional cliff traversal. Again, Karen mentioned this pretty interesting task for babies, right? It's also pretty interesting task for humanoid. Basically, they need to support. And this is like a local manipulation. The robot need to move 1 box from somewhere to a desired location. All right, many tasks. Again, check out the website for more videos. Yeah, we're going to open source code as well. All right, this is part 1. Let's go to part 2, how to go beyond this using learning control in 3 different levels. All right, so I want to start from discussion, do we still need model-based control? Because all the demos in part 1, are trained with model-free sim-to-real reinforcement learning, right? End-to-end, right? Single neural network, just directly output joint angle, that's it. So the results are pretty interesting and promising, but if we take a deeper look, this is what happens on the generalist agility plot, right? If you remember the generalist agility plot. In simulation, every task is pretty good, right? Maybe a few tasks in simulation fails because, like RO exploration problem, like we use PPO, or it could be something like overfitting. But in general, it's okay in simulation. However, when transferred to the real world, first, all task performance drops a lot. And even worse, like some tasks just completely fail. even though it works very well in simulation. And due to the sim-to-real gap, or like fragile to perturbation. For example, the squat stuff, we spend a lot of time. Every time it works so well in simulation, we try to real world, robot cannot squat, it just falls. Yeah, we don't know why. Really, it's kind of still a mystery for us. So in my opinion, the current sim-to-real pipeline have some fundamental issues. So the policy are very sensitive to training environment, like different, how do you set up the seed, how do you set up the contact dynamics, hyperparameter in Mojuko, whatsoever. And the sim-to-real gap is large, unintuitive, and pretty hard to quantify. You never know which task will work, which task will fail. It's very unintuitive. And this procedure requires very tedious reward tuning, curriculum tuning, and domain recommendation tuning. It still relies on GSD, which is graduate student descent. There's no like theory or like, it's just like heuristic pretty much. And it's hard to encode prior physics. In general, this framework suffers from poor sample complexity, and of course, it's unsafe. And also, another thing I want to mention is this procedure doesn't have test time improvement. Once you learn policy from the simulation, it is fixed. You never improve it. This is another big problem in my opinion. All right, how do we go beyond it? I think we still need model-based control, and we should get better tools. And there are many ideas. Today, I'm going to present 3 different levels. Just one level, I'll give you 1 example. In dynamics level, the idea is we directly learn from real world. Can we learn a dynamics model or word model from the real world, right? And you don't need to do sim-to-real. You directly learn something from the real world. And in the policy and action level, and can we do something beyond N2 and RO? Can we use some good structure from model-based control and physics, have structure and hierarchical RO and control? And on the program level is, can we enhance existing control program like MPC using ideas from learning? So in my opinion, the role of control here is threefold. So first, it brings structures and priors from physics and dynamics. And the second, I think it guarantees or enhance safety, robustness, and efficiency. And third, I think personally I'm really thinking about a lot, is control allows some test time scaling. I think the robot learning community has been focusing too much on offline scaling. I think model-based control, model-based approach enable some test time scaling via online adaptation, online planning, and online optimization. All right, let me start from the dynamics level. The first example is my PhD work called neural control family. It's very old, so I'm going to do very quick. So the key idea is, okay, for drones, we start from this the black partner equation, which is standard Euler Lagrangian dynamics. But there's some residue unknown dynamics, right? The F part, which is very nasty. For example, aerodynamics, things like that. So we basically use the deep neural network F hat to approximate this unknown residue dynamics. Once we learn the dynamics from the real world, we design a nonlinear controller, pi, as a function of F hat. And the detail is we need to regularize the Lipschitz constant of the neural network to guarantee Lyapunov stability. And the threshold is from control theory. And this pipeline gives some interesting result, like single agent, we have a neural lander, the drone can precisely land to the ground. And the multi-agent, we have a neural swarm, the F depends on neighbors. And in the adaptive control setting, we have a neural fly. The F here is a time variant function. We need to do offline meta-learning and online adaptive control. It's basically my PhD result. It works well for drones. And after joining CMU, I've been thinking about, can we generalize this framework to transformer, to large-scale learning? And the answer is yes. So the project I want to introduce is called AnyCar. Basically, we're trying to learn a universal vehicle dynamics. So AnyCar is a transformer-based vehicle dynamics model that can adapt to various cars, environment, all different types of state estimation method via in-context adaptation. And this figure shows some cars, environment, task, and the state estimation method it can adapt to. The interesting is like the white hair here. The white hair is very interesting. It's 3D printed plastic hair to stress test adaptability. We basically like 3D print very, very bad hairs to stress test how much the model can adapt. Once we learn the model, by the way, we didn't do RL here. We use sampling-based MPC for control once we learn the model. Before talking about the pipeline, I want to show you some result. And any car can enable very interesting drifting in the wild. This is drifting in the evening in the wild, again, with plastic tears. So the model doesn't know, we switch the tire to with a plastic tire and enable this drifting, pretty high speed, 4 meters per second each drifting. Here it can adapt very rapid adaptation to different slope and different terrain, right? It can track the trajectory pretty accurately on different terrain from concrete road to grass road. And here is adapting to a very large payload. It's towing a very large object. Need to adapt to all this friction and its payload. So how do we do that? How do we do that? So the model input is a k-step noisy state action history and h-step future action. And the model output is h-step future state. So it's basically a sequence-to-sequence model conditioned on h-step noisy history, right? It's a sequence-to-sequence model. You're predicting h-step future state as a function of h-step future action. Because we're going to do MPC, right? You need this kind of sequence-to-sequence prediction. How do we train that? We learn a lot of lessons from NLP. We collect a lot of data in simulation. We collect 100 million data points in very diverse simulation. From a very simple simulator, DBM, to a Mujoko, to SXSim, all the way to this F1 level simulation. On the right is Sati Corsa, is F1 level, very realistic vehicle simulator. Right, this is a large simulation data, 100 million. We also collected like a few shot real data for fine tuning. This is like only 20K, a little compared to the pre-training data set. This is the data. Once we have data, we basically learn a kind of like transformer, right, corresponding to this sequence model. What is interesting is to make the transformer model robust, we add some mechanisms like mask out, noise, and attack. Mask out means we randomly mask out certain state and action in the history. And noise means we adding Gaussian noise to the history. And attack means we add like artificial large attack in the history. All this stuff are trying to mimic what happens from real-world state estimation and to make it robust to real-world state estimations. And we have a lot of similar designs from like language model. Actually, we have a tokenizer, position embedding. We also have similar designs. Check out the paper for details. We also open source the code, by the way. Yeah, and I think the lesson from this project is learning dynamics can scale to transformer and can adapt very well different robot, different environment via in-context adaptation. So let's go to the policy level. Again, the structured and hierarchical reinforcement learning control. So in this project called continuous jumping over discrete terrain, we actually didn't do end-to-end reinforcement learning. We actually did a hierarchical reinforcement learning control. So reinforcement learning here only output the high-level reference trajectories. It outputs center of mass reference acceleration, Q double dot breadth. And we use QP, quadratic programming, which is basically MPC kind of thing, to track this reference trajectory, right? The pi QP here optimize ground reaction force, right? And this enables this interesting continuous jumping. It can jump continuously over stepping stones. By the way, all the video here are real time. I didn't speed up. And it can jump continuously over stepping stones. And for the first time, we can enable this robot jumping over stairs. That's something dog can do, but very hard for robot dog, right? And due to, because we have a QP program, it's very robust. It can do some self-correction from failure. Like here, if you can see in the second video, it has some stumble, but can quickly recover. All right, and another example in structure and hierarchical reinforcement control is safety, right? For safe robot learning, it's also very common. Like we have reinforcement learning as a high level. And in the low level, we have a safety filter, right? The safety filter is kind of like safeguard the RO policy, right? And the example is this project, which is RSI's outstanding student paper finalist called Agile but Safe. So in this video, the robot dog can do very quick, very fast collision avoidance, in very narrow corridor. It's very reactive. And if you see the LED, the green means reinforcement policy is just control the robot, and the red means the safety filter is taking over control. I switch between two policies. Yeah, it's very robust on winter Pittsburgh and different terrains. Okay, I'm gonna switch to my favorite part, which is here. It can, collision avoidance with different, you swing your leg, it can dodge. You swing your leg, it can dodge. It's very reactive. And you can even play this hide and seek game with the robot. Yeah, and it's also very robust to payload and and perturbations. You have to bully the miserable robot all the time. Yeah. All right, so this is fully onboard and fully autonomous. We use depth camera as the sensing, and it's very fast, up to 3 meters per second, and it's safe and robust, and also open source the code from training to hardware deployment. All right, I have 5 minutes, so I'm going to the last part. It's perfect timing, actually. The program level. It's like we neither learn dynamics nor learn the policy. We use learning to enhance whatever already useful in control. So the particular example I want to present is how do we enhance model predict control using learning. If you are not familiar with the model predict control, it's basically solving this H-step optimal control problem. So the control sequence big U here is the decision variable. And the J here is the total cost. The C here is a single step cost. X is a state, U is a control, F is the transition dynamics, right? And for example, it's a drone trajectory tracking problem. So the main challenge of MPC is this problem is hard to solve, especially for gradient-based method, especially with the policy, when the problem is highly non-convex or even discontinuous. For example, in contact-rich problem, your F is not even continuous, right? Using gradient-based method to solve this is very hard. So sampling-based MPC, for example, MPPI, is alternative. However, sampling-based MPC in general has limited agility in contact-rich problems and little theoretical understanding. So to make sure we're on the same page, I want to just briefly introduce what is MPPI. MPPI is actually quite straightforward. What you do is sampling on GPUs, right? You sample a lot, like n control sequence from a Gaussian, and the mean is U, the current is sigma. Sample a lot of thing on GPU. And the second line here is you rule out all these samples in massively parallel simulation to evaluate cost, like J1 all the way to Jn. And then you compute the weight using this kind of like a softmax thing. We can call this Nobel Prize winning equation because it has deep connection with Boltzmann machine and energy-based model, right? Yeah, but the basic intuition is the larger cost this sample has, the lower weight you're going to assign to this sample. And then you have this exponential step. And lambda is the temperature, control the sensitivity. And finally, you update your control, right? Your control is just like the weighted sum of all the samples. Okay, to better understand MPPI, I need to introduce some notation very quickly. The first thing I need to introduce is the P0, which is the target distribution. It's basically like proportional to E to the minus G over lambda corresponding to the original G, right? And again, this is still a non-convex, even discontinuous distribution. It's an original target distribution. You're trying to optimize. You're trying to reach the maxima of this figure. And the second distribution I need to introduce is corrupt distribution. It's basically a convolution between P0 and the Gaussian sampling kernel. Right? We call it P sigma. For example, this figure gives you 4 different P sigma. P1 is with small sigma, and P4 is with large sigma. Right? The large sigma you have, and the new distribution P sigma is going to be like smoother, but further away from the original one. Right? You can think of P sigma as a convexification or smoothness of P0. Okay, why I need to introduce this? Because we proved something very interesting in my opinion. In our newest paper, we prove MPPI is basically doing something like one-step diffusion. So we proved the following result. If number of samples goes to infinity, the output from MPPI is basically a one-step update with a sigma conditional score function. I mean, this score function is basically gradient of log P sigma. It's gradient of log likelihood of P sigma. And again, P sigma is a convolution between original one and some sampling kernel. So it's roughly doing a denoising step, which is very interesting. If you compare with the Langevin dynamics in score-based diffusion model, these two equations are basically the same. So in Langevin dynamics, the S sigma here, the S theta here is a learned score function, conditioned on noise level. The only thing difference is in Langevin dynamics, it has white noise ZT, because in diffusion model, you care about the coverage You want a diversity in the output, but in MPPI, you don't. You only care about the optimal point. All right. So once we prove this, we realize MPPI means a very important mechanism in diffusion, which is annealing, right? And diffusion works, a large reason is annealing. In diffusion model, you always start from large noise and gradually anneal down to small noise. This is why this kind of image generation works, right? And can we do the same thing for MPC? And the answer is yes. And we propose diffusion-inspired annealing for lag MPC, right? I mean, it's actually very straightforward. In standard MPPI, if you have a very large sampling kernel, you convert very fast, but you have a bias. I mean, if you have a small sampling kernel, you got stuck in local minima. And in our Dell MPC, you can do this annealing all the way to the star. Yeah, control the sampling kernel. Yeah, and what is even more interesting is in MPC, you are doing receding horizon. You can leverage the temporal structure MPC to do this step by step, right? And the UH here experience the whole diffusion process on the fly. Okay, just want to quickly show the result, the last slide. And this is like visualization of the annealing, where we start from noise trajectory and all the way to a preset trajectory. And Dell MPC enable this preset jumping with payload. Yeah, and we can also do like human local manipulation. Yeah, all these videos are training free. No, we don't need data or training. Yeah, so basically we enable 50 Hz talk level control using full order dynamics. We directly roll out in parallel simulation. We don't need anything like reduced order modeling, local approximation, or predefined control sequence. And it's training free, plug and play, and zero-shot adaptation, right? You add a payload, you change task, because it's model-based. It doesn't care, it can adapt, just zero-shot. And we only need like 4 or 7 to 7 reward terms for each task. And I think a takeaway is skill online search, skill online optimization is also powerful. All right, we can also generalize to trajectory optimization. Similar idea, we can solve this humanoid and push T task without any data and training. Right? If you know, push T is a pre-training task in LFD, but we can solve without any data. All right. Summary very quickly. I present this generalist and agility plot. In part 1, I present symmetry reinforcement learning. In part 2, I discuss the limitations and how to go beyond it via learning control. And I think a big takeaway is we need structure scaling with dynamics and physics. And all the reference and open source code can be found in my lab's webpage. And thank you very much. Yeah. Sorry, if you want a slides, just scan the QR code. We have a PDF. Yeah, if you want.
Thanks. I just had a question about generalizability. So, so for different tasks, different modalities might matter, right? Not every modality might have the same impact or importance in every task. So when you train your model in order to improve generalizability, do you keep the number of modalities the same across all tasks, or do you happen to use different modalities, and how impactful do you think it is?
That's a very, very good question. I like it a lot. I think that's another big challenge in generalist robot I didn't cover today, unfortunately. I don't think robot learning community has figured out a way to have adapt to number of modular in terms of modality. Either we all the way do vision, tactile, everything together, always select some of them. I don't think we have. Maybe some people have done that, but I feel that's pretty challenging. And in all the video I showed today, the number of modalities fixed. You either do vision proprioception, or you do just proprioception. Yeah. I think that's a very interesting point. Yeah.
Thank you very much.
Ben. Yeah.
Let's give him another round of applause. Thank you.